Hello guys, and welcome to today's AB Math class, your hub for learning anything related to math. In today's class, we are going to be going over 4 main topics. First, we're going to be going over how to parametrize a surface. Second, we're going to be talking about vector surface integrals. Third, we're going to be talking about Stokes' theorem. And finally, we're going to wrap the video off with a lesson on Gauss's theorem. So without further ado, let's jump right into today's lesson. So right now, we're going to look at how to parametrize a surface. But before we do that, let's go back to what we already know. And what we already know is how to parametrize a space curve. And the way that we did this was by defining a function r in terms of a single variable t. And basically what we did is that we defined each component of r, each component of the vector function r in terms of a parameter t, by saying that the x component was x as a function of t, the y component was y as a function of t, and the z component was z as a function of t. And in doing so, we were able to parametrize a space curve in terms of a vector function r of t. But now what we want to do is parametrize a whole surface. And in order to do this, we're going to need 2 parameters instead of just a single t. And by saying this, I mean that we're going to need 2 parameters which we are going to define as u and v. And we can say that their vector function can be defined as r of u and v. And we see here that rather than just have one variable or one parameter, our new r of u of v for parametrizing a surface has 2 parameters known as u and v. But similar to our parameterization of a space curve, for this parameterization of a surface, we are still going to define the x component, the y component, and the z component all in terms of u and v. And hence, we're going to get that our parameterization for a surface would be x as a function of u and v for the x component, y as a component of u and v for the y component, and z as a function of u and v for the z components. And hence we have our vector valued function for our parameterization of a surface. And looking specifically, we can say that this vector valued function is defined on a region which we'll call D. And we can say that this region D is on the UV plane, as our 2 parameterizations or parameters for this vector valued function are u and v. But before we talk about that, let's just get down to the basics. And we can say that for this vector valued function, we can say that the x component is x as a component as a function of u and v, y is y as a function of u and v, and z is a function of u and v as well. And these will be known as our parametric equations. Let me just write that out. There. And hence we have our x, y, and z components all for a function r, and we can say that this holds true for any point x, y, z in the real number or the 3D space. Now going back to our region D, over which r is defined, if we draw it out by drawing out our UV plane, let's label our axes like that. We can define any region D, as I will do so right now, and we can label that D. So what this tells us is that we can define any points in this region D in terms of u and v. But if we want to look at our parametric surface, which we will call S, we're going to have to draw it in 3D space, because instead of just having one variable as we did for our space curves, since we're defining and parametrizing a whole surface and we have two variables, our R of u and v will be defined in a 3D space. And basically what RU of v tells us is what our surface S will look like. Because if we draw our surface S right here, we can draw it sort of like a 3D object. Sorry, my 3D is not the best. But basically what we can say that R as a function of u and v, if we graph it for every point that we had in this region D, and we say that this point right here is R as a function of u and v, and we graph that for every point in the region D, we will get a surface S. And hence, when we look at our parametrization for our surface S, we basically see that in defining this, our vector valued function, or our parametrization of a surface, we're basically saying that by plotting every point in the region D being this right here, we will get our surface S. And that's how we are able to parametrize a surface. Alright, so now that we have learned how to parametrize a surface, let's try a practice problem to test our understanding of what we have learned thus far. And to this, we're going to look at number 4 on the review sheet. And if you don't have the review sheet, that is totally fine. I'm going to write out the problem for us right now. And basically what it's asking us to do is write a vector description or a parametric representation. Sorry, I'm going to write this out. Representation for a sphere with radius 3. I'm going to abbreviate radius to be R with 3, and centered at the point, let's go to the next line, 1, 2, 3. And basically what we want to do is use what we learned here for parametrizing a surface to basically parametrize the sphere with the radius 3 centered at the point 1, 2, 3. And before we do anything, I'm going to go ahead and draw our surface for us. So to do this, we're going to have to draw our 3 coordinate plane, x, y, z, and we're going to graph our point 1, 2, 3, which our sphere is centered at. So let's define this to be 1, this to be 2, and there. We have 3. So to graph this, we're going to find first our point in the 3D plane. Let's do that right now and draw that up. So our point is going to be right there. And just to make everything a bit clearer, I'm going to go ahead and erase all these lines that we used to be able to find this point. And here we have our points 1, 2, 3. And we know that our surface is a sphere with radius 3. So let's go ahead and draw a sphere with radius 3 around it, roughly like that. And we can say that this has a radius 3. So the next step I want us to go ahead and take is actually writing the function of our sphere as we would if we were just using rectangular coordinates. And the way we do this would say x minus 1 squared plus y minus 2 squared plus z minus 3 squared is equal to our radius squared, which in this case we know is 9. So right there, we have our rectangular equation for our sphere. But what we want to do right now is find the parametric representation. And to this, I'm going to first start off by going over how to find it for any sphere. And we can define the sphere as being x squared plus y squared plus z squared is equal to a squared. And we know from our spherical coordinates unit that rho squared is equal to x squared plus y squared plus z squared, which in this case is also equal to a squared, so we can go ahead and say that rho is equal to a. And because this, we can say that rho is equal to a, as I already said, and we can set this rho, or the parametric equations, in terms of phi and theta. And we're going to say that much like our sphere up here, for number 4, this is going to be a full sphere, no hemisphere, no quarter of a sphere, and we can say thus that phi goes from 0 to pi, and theta goes from 0 to 2 pi. Because as we know from our units on spherical coordinates, theta represents this value down here, and then rho represents this horizontal value right here, and basically this is what we get when we want to find the phi and theta values for a full sphere. So next off, what do we need to do? We need to find our parametric equations for our sphere. And because we've already gone over the spherical coordinates unit, we can say that x in this case is equal to a sine phi cosine theta, y is equal to a sine phi sine theta, and z is equal to a cosine phi. And this would be our parametric equations in terms of phi and theta for any sphere. In this case, x squared plus y squared plus z squared equals an arbitrary radius a squared. And hence we have our parametric equations for this arbitrary sphere. And if we want to write out the parametric equations for this surface, we can say that u in this case is equal to phi and v is equal to theta, and we can say that r in terms of phi and theta is equal to a sine phi cosine theta I plus a sine phi sine theta for the y component and a cosine phi for the z component. And right there, that is our parametric equation or parametrization for any random sphere, any full sphere centered at the origin with an arbitrary radius a. Now let's go back to our problem. We know that in our case, our sphere, not centered at the origin unfortunately, is instead centered at 1, 2, 3. But this is not going to be a problem for us, because we can say that much like in this equation right here, we basically have that. We can say that our x minus 1 is equal to some arbitrary constant. Sorry, not constant. We can attribute x minus 1 to some variable, which in this case, let's choose the letter S. Let's go with S. We can say the y minus 2 is equal to P, and then we can say z minus 2 is equal to G. And right there, we have our rectangular equation for our sphere put into, I guess, other variables. And because of this, we can write our sphere centered at 1, 2, 3 in terms of the rectangular coordinates s squared plus p squared plus g squared is equal to 3 squared, which in this case can be 9. And when looking at this rectangular equation, we see that it is very similar to this rectangular equation we had for any arbitrary sphere centered at the origin with a radius a, which in our case, we can say that a is equal to 3, as 3 is our radius. So then moving ahead, we can use this parametric equations for our x, y, and z components, since we have almost an identical equation for the sphere, any arbitrary sphere centered at the origin, which we have already defined. And we can go ahead and say for s, we can say it's 3 sine phi cosine theta. For p, we can say that it's 3 sine phi sine theta. And finally, for g, we can say that it's 3 cosine phi. And just to be clear, these values right here, these are just taking the place of the x, y, and z in this equation. But right now, what we're going to do is that we're going to put it back in terms of x, y, and z, and so that we're going to use some simple substitution by substituting these values back in. And in doing so, let's just copy these values so that we don't have to write them out again. We can say that x minus 1, substituting in for s, y minus 2, substituting in for p, and z minus 3, substituting in for j, is equal to these values. In doing some simple math, we then get, let's copy this again, just so that we don't have to write it out again. We can erase all these values as we're going to add them over to the other side. But in doing so, we are going to get our parametric equations for this sphere centered at the point 1, 2, 3, and with a radius 3. And if we want to put it in terms of our r of u of v, which in this case would be r of phi and theta, we can say that our vector valued function for r in terms of phi and theta would equal to, let's copy these over again, just so that we can save some time. That's right. For the x component, plus, sorry, let's write that on the same line, plus let's write some parentheses again. And right here, we're going to have to go onto the same line, still the same equation right there. And that is going to be our vector valued function for our parametrization of our sphere. And most importantly, to finish this off, as we defined earlier, these are going to be our phi and theta values. And right here, we can say that phi goes from 0 to pi, because as we know from our spherical coordinate units, these would be the values of phi and theta if we wanted to have the full sphere. Alright, so now let's go ahead and look at what the graphical representation of this would be. So going up, we can copy this and paste it right here. And so basically what we see is that this parametric equation right here is basically the parametrization of this sphere as we drew earlier. But let's look at what happens if we set phi and theta to be constants. So starting off with phi, if we set phi equal to some constant c, what we are going to get is that we are going to get grid curves, which basically occur when we set either u or v equal to some constants. And since our u here is phi and our v here is theta, we can basically say that when u or phi is constant, we're going to get lateral grid curves, or lateral circles parallel to the xy plane. And when we look at the grid curves for when v is constant or theta is equal to some constant, basically what we are going to get is that rather than getting horizontal circles as we did for when we set phi equal to some constant, instead we are going to get something called meridians, which are basically equal to semicircles. And they basically are going to go around this whole circle. Sorry, this should join back right here. We can draw like some imaginary axis, right? And I guess kind of pretend that they go from the top to here. And as we set theta equal to some constant value, whatever it be, whether it be 1, 2, 3, we can basically say that it is going to form meridians, which are going to be semicircles connecting the north and south pole. And basically, that is going to be what our graphical representation is going to be for if we set theta equal to some constant. That is going to be the grid curve. We are going to get meridians, and if we set phi equal to some constant, the grid curve we are going to get is full, not just semicircles this time, full circles with a constant latitude, or full circles with phi equal to some, again, random constant, whether it be 1, 2, or 3. We are going to get a horizontal surface. So I guess that's it. So let's just recap it a little bit to go over some points that we might have missed. So basically, we were trying to find the parametric representation for a sphere with a radius 3 centered at 1, 2, 3. The first thing we went ahead and did is that we went ahead and graphed it. We see we got a pretty decent graph, and we're going to go ahead and write the rectangular equation, which we have right here. And then we went ahead and found the parametric equations and parametric representation for any arbitrary sphere centered at the origin with the radius a. And basically what we did is that we found that it would follow this parametric equation. And then what we went ahead and did, because our sphere was not centered at the origin, we went ahead and put in almost substitute variables, we can call them, and say that we substitute them in for x minus 1, y minus 2, and z minus 3. Sorry, this should be z minus 3 for our equation with s, p, and g respectively, and we got this equation, which looks a lot more similar to the equation we have up here. And because we went ahead and did that, we could define our new equation for our sphere, which looked, again, very similar to that in terms of the same parametric equations that we got for any sphere centered at the origin. And in our case, our a was equal to 3, and because that we got the s is equal to 3 sine phi cosine theta, p is equal to 3 sine phi sine theta, and g is equal to 3 cosine theta. And then we went ahead and substituted back in the values that we substituted in for s, p, and g initially. And when we put the 1, 2, and 3, added them to the other side respectively for x, y, and z equations, we were able to get our parametric representation for a sphere centered at 1, 2, 3 with a radius of 3. And then finally, to go over again, this equation would represent the whole sphere. If we were to look at the grid curves with, let's say, phi with some constant, we get full horizontal circles parallel to the xy plane. And if we set theta equal to some constant, we get meridians, which in this case would give us semicircles connecting the north pole with the south pole all around the sphere. And yeah, that is how we solve number 4. Hello, sorry for the change of location, change of setup, but basically what happened is that my screen recording, my Zoom, everything like that, it wasn't working, so I decided to change up my setup. And because of that, I have already recorded and wrote down our notes for our vector surface integrals, but unfortunately it didn't record well. So we're just going to go over them again to make sure that we understand it well. So starting off with our vector surface integrals, we must first define what an oriented surface is. And in order to do this, I'm going to draw some arbitrary surface S. And basically what we're going to say is that because we can define a tangent plane at S, right? At any point, we can say that we can define two unit normal vectors at that point on that tangent plane. And what we're going to call these two unit normal vectors are n1 for the upward oriented one, and then n2 for the downward oriented one, right? And basically we know that the only difference between n1 and n2 is that they have opposite directions. And because this, we can say that n2 is simply equal to the negative of n1. Now, this is important because in order to find the orientation of a closed surface, which I will define next, we must have the unit normal vectors. And so speaking of unit normal vectors, let's again talk about what unit normal vectors are closed surfaces. Talking about closed surfaces before we go on to talk about what surface integrals for vector fields are, we're going to talk about what closed surfaces are. So let's imagine we have some surface S. And basically what a closed surface says, the definition of what a closed surface says is that the surface S must be bounded or have a boundary of some solid region E. And a great example of this is a sphere. As we can see here, we can say that our solid region is our solid sphere, and hence we can say that our surface S is a closed surface. So when looking at our closed surface, right, we can say that its orientation is based on its normal vectors. So looking at our n1s or our unit normal vectors that are pointing outwards, right, we can say that the surface S has a positive orientation, right? If the unit normal vectors are pointing outwards from E, or as we look at this diagram right here, they are our n1s. And then we can say that our surface S has a negative orientation if it has our normal vectors pointing inwards or towards our region E. And looking up here, we can say that it is our n2s. So based on that, based on the normal unit normal vectors for our closed surface, we can define what the orientation is. So now let's move on to our surface integrals for vector fields, or our vector surface integrals. Because we're doing it over a closed surface, we must first define what the unit normal vectors are before we go ahead and find the formula for our vector surface integral. And basically what I'm going to do is that I'm going to find two ways that we can find our unit normal vectors. So let's go on to our first one. We can define an arbitrary function z, and we can give it the value g. We can set it to some function g with respect to x and y. And then we can go and define a new function f of x, y, z. And we can say that f is equal to z minus g of x, y. And based on the definition we had right here, we know that f is simply equal to 0. And because of this, because we have f of x, y, z is 0, we can say that its gradient is basically orthogonal, or it is the normal vector to our surface because of f of x, y, z is 0. But we must recall, before we can go ahead and say this is the unit normal vector, right? That up here I said that we need the unit normal vector, and the gradient only gives us a vector that's orthogonal. And in order to make sure that we have the unit normal vector, I'm going to say that n is equal to the gradient of f divided by the magnitude of f. And because I go ahead and say that, we can assume that this is the unit normal vector. And just plugging in some values for the gradient f, we get this value or this simplified value for our unit normal vector, which as we can see here is minus partial g with respect to x for the x component, minus partial g with respect to y for the y component, plus k, and then divided by the magnitude, which is just the root of the partial g with respect to x squared plus partial g with respect to y squared plus 1. Now that's our first way of defining our unit normal vector. And before we move on to the second, I must note that if we look at the z components here, we note that it is positive, and that is because our normal vector, we generally want it to be as we define in the positive orientation. And basically what I mean by this, right, is that not necessarily that our vector is pointing upwards or downwards. We just want it to be in the positive orientation. And normally by this, we will have an upwards oriented normal vector, unit normal vector, but we can also have a downwards oriented unit normal vector. In order to get this, we're just going to take the negative of this unit normal vector. Now moving on to our second way of finding our unit normal vector, we're again going to go back to our parametrization that I was talking about earlier, and we can say that r of u of v is equal to x of u and v for the x component plus y of u of v for the y component plus z of u of v for the z components. And basically what we can recall, right, is that r partially r with respect to u cross partial r with respect to z, this is basically going to give us the normal to a tangent plane at a particular point. And going back up to our diagram, we see that at this point, ru cross rv basically gives us these normal vectors on that plane at that specific point. Now again, we need to find the unit normal vector, and as always, we're just going to divide by the magnitude of ru cross rv, and in doing so, we get this second definition for the normal vector. Now that we have our definitions for our unit normal vectors, let's go ahead and define our vector surface integral. And basically what I'm going to say that our vector surface integral is simply equal to the double integral over surface S of f dot the normal vector ds. And basically what this gives us, right, is that for a vector field with a normal vector, that unit normal vector that we know is n, right, then we know that the surface integral of f over the surface S is given by this equation. And we can also just call this the flux of f across S. And so this should generally give us the equation for our vector surface integral. But just to make problem solving a bit easier, I'm going to go ahead and plug in our unit normal vectors. So for the first situation, we know that we can just define z as g of xy as always, and we're going to go ahead and define our vector field f to be pi plus qj plus rz, and that this is oriented in the upward orientation. And just to note, if we want it to be in the downward orientation, we simply just take the negative of the normal vector to just change the signs. So plugging in our normal vector from all the way up here, this value right here, and plugging in over here for our normal vector, we get that we have our vector field dotted with our normal vector value, and then we can also substitute in our ds value, which from previous chapters we know is the root of partial g with respect to x squared plus partial g with respect to y squared plus 1 dA. And when we simplify this, we see that these two square roots cancel out. We get that our integral is simply equal to the double integral over some region D of our vector field f dotted with our basically our gradient now dA. And when we simplify this, we get this simplified version for our vector surface integral, which is the double integral over some surface d of minus p times partial g with respect to x minus q times partial g with respect to y plus r, all of that times dA. Now going on to our second situation, we see that we can again plug in for our normal vector, we can plug in the value we got for our second situation, which would be RU cross RV over the magnitude of that. And when we do that, once again, we see that these values cancel out and we get F dot RU cross RV dA. And that is basically what we get for the simplified version of our our vector surface integral. All right, so now let's move on to solving a problem. All right, so for our sample problem, I want us to go ahead and look at number 28 in chapter 16.7 in our textbook. And if you don't have our textbook, that's totally fine. I'll just write out the problem right here. And basically what we have is some vector f of x, y, z is equal to y, z, I plus z, x, j plus x, y, k. And then we know that S is of the surface. Oh, that's a weird S. S is of the surface. Sorry, is the surface. Is the surface. Z is equal to x sine y. And we know that x goes from 0 to 2, and y goes from 0 to pi. And we also are given that it has an upward orientation. All right, so now that we have our problem copied down, let's look at what we have. So first off, we're already given our z value, which in this case we know is going to be x sine y. And we also know that we are going to have an upward orientation, meaning that for our normal vector equation that we had up here, we're not going to have to take the negative or anything like that. So looking at what we have, we can say that the first variation, our vector surface integral, makes the most sense. So I'm going to go ahead and copy that equation to down here. So basically what we have, looking at our F or vector field equation, we already have our P value, we also have our Q value, and we also have our R value. And looking at our Z, the only thing that we need to do is solve for G of X and G of Y, which in this case, finding partial G with respect to X, we find it's just equal to sine y, and then partial g with respect to y, we find is just equal to x cosine y. So in solving for that and looking at the equation we have right here, we can say that we're ready to solve our vector surface integral simply because we already have our bounds solved or given to us, which is very nice, but oftentimes this might not be the case. So let's go ahead and plug in our values into this equation. So first, let's start with our dA and our bounds. So the way I want to solve this personally is I want to go dx dy. So that means y is going to come second and x is going to come first. And then we can just put our dx dy over here. So now let's go to the actual integrand. We already have our p value, which is right here, and we can say minus, what was it, yz times partial g with respect to x sine y So it looks like this dx dy is going to have to move all the way over here. Minus q, which right here, which is minus zx, times partial g with respect to y of x cosine y. Looks like this dx dy is going to have to move all the way to the end of the page. And then minus a final r to fulfill our equation, basically. Sorry, not minus, plus. And there we go. We have our vector surface integral. Evidently, my dx dy got cut off, but not to worry, we have that in. So now all we have to do is the fun parts. Sorry, before we do that, we need to take one more step, which is plugging in our z value, right? Because we're only integrating with respect to x and y, but we still have z's in here. And to do that, we can simply just plug in our z is equal to x sine y. And when we do that, when we simplify that out, we're going to get minus y times, what was it, x sine y. I'm going to go ahead and simplify that, combine those terms. We're going to get x sine squared y minus z times x cosine y. We already know that this is x squared. So we can say we're going to multiply by an x sine y. So this is going to become x cubed sine y cosine, sorry, I don't know what happened there, cosine y. And then there's no z terms here, so we can just say plus xy dx dy. And that is our integral ready to solve. And now we're going to get to the fun part. So first off, we're going to integrate with respect to x, since dx comes before dy. And when we do that, we're going to get minus 1/2 yx squared sine squared y minus 1/4 x to the fourth sine y cosine y plus 1/2 x squared y from 0 to 2 times dy. We're running out of space here, but not to worry. Then we're just going to plug in those values. Since our bottom value is 0, we can see that we don't necessarily have a sine or cosine. And when we plug in 0, all of these values are just going to give us a 0. So I'm just going to assume that because we're just going to have 0 when we plug in 0, I'm not going to write out 0 minus 0 plus 0. Instead, I'm just going to go ahead and plug in only the two values. So when we do that, what we get is that we get minus 4/2. So minus 2y sine squared y. 2 cubed divided by 4, we know 2 squared is just equal to 4. So 1/4 and 2 squared. 1/4 and 2 squared just cancel out. So we're just going to have 2 squared by the end of this. So minus 4 sine y cosine y plus, again, just 4 divided by 2 plus 2y dy. And that is what we're going to have. So now we have to integrate with respect to y. Now, in order to do this integration, we're going to need a very important piece of information, which in this case is going to be the sine squared y is equal to 1 minus cosine of 2y divided by 2. So because this, we can just plug that in right there. And when we do that, we're going to get integral from 0 to pi of minus 2y times 1 minus cosine 2y over 2 minus 4 sine y cosine y plus 2y dy. When you do that, we can simplify. We can just cross out those 2's. And when we do that, we're going to get this integral from 0 to pi of minus y
plus y cosine of 2y minus 4 sine y cosine y plus 2y dy. We can combine these terms, and when we do that, we get integral from 0 to pi of y cosine 2y minus 4 sine y cosine y plus y dy. And additionally, we're going to have to go ahead and make another substitution to simplify this right here. And in specific, we're going to say that sine of 2y is equal to 2 sine y cosine y based on the double angle formula. And when we plug that in, we see that this value right here is just equal to double of this. So when we simplify this out again, we get y cosine 2y minus 2 sine 2y plus y dy. And finally, we are just about ready to integrate this. So to make this a little bit easier for myself and us, I'm going to split this up into two integrals. One y cosine 2y dy minus integral from 0 to pi 2 sine 2y plus y dy. Now, this integral right here, relatively easy to solve. Actually, let's go ahead and split this up into three integrals, just because this one right here is going to require a little bit more work. All right, so we can say u is equal to 2y using u sub, du over dy is equal to 2. So dy is simply equal to du over 2. And plugging this in for dy right here, we see that our 2 and 1/2 cancel out. So we simply have minus the integral from 0 to pi of sine u du. And then we know that this integral, quite straightforward. We know that the integral of sine u is minus cosine u. And since we have the minus right here, we can just simplify this out to cosine u. And since we know our u is 2y, we can say cosine of 2y from 0 to pi. And then bring this down. This, again, a very simple integration of integral of y from 0 to pi, don't forget your limits, would be 1/2 y squared from 0 to pi. Now, just to end off these two right here, we're gonna plug in our values. We know cosine of 2pi, minus cosine of 0 plus, again, this is, if we plug in 0 for this, it's just going to give us 0. So I'm not going to plug that in. Instead, I'm just going to get 1/2 pi squared. When we look at this, we see that this is equal to 1, this is equal to 1. So we get 0 plus 1/2 pi squared. And this is only for this portion of the integral. Now we need to move on to this portion, which is going to need a little bit of parts. Parts to integrate this. And if we recall correctly, we know that for parts, we know integral of u dv is equal to uv minus integral v du. And what we can go ahead and say is that u dv is equal to this, and that is equal to that, uv minus integral v du. And what we can say is that we can define u to be y and dv to be cosine 2y. And then when we find du, we find that simply equal to dy or 1 dy. Let's not forget the dy right there. And then when we take the integral of this, we get dv is equal to 1/2 sine of 2y. So there we go. We have our u and v values, and our du and v values again, and then we can go ahead and plug it into this. So what we're going to do is that we're going to say u times v is equal to 1/2 y sine 2y minus v again, 1/2 sine 2y. So I'm going to move this over just because we're running out of space here. And then we know du is just equal to dy. So there we go. The only thing we have left to do is to integrate this. And again, we know the bounds are 0 to pi. And as we did over here with the integral of sine 2y, we can simply look over here and see that we did u sub. We said u is equal to 2y, du over dy is equal to 2, hence dy is equal to du over 2. But not like before, our 2's don't cancel out. Instead, when we multiply 1/2 times 1/2, we get minus 1/4 integral of sine u du. But much like before, integral of sine u is minus cosine u. We see that we have this minus right here. So our minuses cancel out. And instead we get plus 1/4 cosine 2y, not to forget this part up here, 1/2 y sine 2y. And we're going to value all this from 0 to pi. And there we go. We're at our final step for this question. And finally, what we can do when we plug in 0 or pi for this value right here, we know sine of 2 pi is equal to 0. And then sine of 0 is also equal to 0. So regardless of either of these two limits that we plug in, we get 0. So I'm kind of just going to cross that out. So now looking at cosine of 2, 1/4 cosine of 2y, we have 1/4 cosine 2 pi minus 1/4 cosine of 0. And much like over here, we know cosine 0 is 1, cosine 2 pi is 1. So these values simply cancel out, boom, boom, and we get 0. So finally, our answer is a combination of all of this. It's 0 plus 1/2 pi squared. So in entirety, our answer is simply 1/2 pi squared. And there we go. Now, let's just check over this really quickly to make sure we didn't make any mistakes, as this was, as we can see, a very long question. We see that in order to solve this, we used the second variation of our vector surface integrals, as we defined from our first unit normal vector, as we were given our z value, and we were also given our positively oriented vector field. And based on that, we could simply find the partial g with respect to x and partial g with respect to y, plug those in. We were already given the limits, which is quite nice. And because of that, we could simplify, and when we simplified, we got this. Now looking at our substitutions, we see that we used some trig functions in order to get our values. In specific, sine y is equal to 1 minus cosine 2y over 2, and also sine 2y is equal to 2 sine y cosine y. And when we did that, we got this value, integral from 0 to pi of y cosine 2y minus 2 sine 2y plus y dy. And once again, the integration was not the nicest, but we split this up into two integrals, one for parts and one for just normal u sub and regular integration. And when we do that, checking our limits, actually making sure our integration's right, u sub looks all correct. Using our limits, we see that the only one that would work would be this one, as cosine 2 pi, cosine 0 are the same, so they cancel out. And 1/2 times 0 squared is just equal to 0. So the only value we should get is 1/2 pi squared. And then looking at our parts integration, uv Our parse looks correct as well. Using the same use of as above, we see that again, we get cosine 2y. And as we saw here, that would just equal 0. So that checks out. And then for sine 1/2 y sine 2y, even though this won't necessarily, the y value itself won't necessarily be 0, the sine 2y at both pi and 0 would be 0. So this checks out to be 0 as well. So finally, combining them, 0 plus 0 plus 1/2 pi squared is equal to 1/2 pi squared. And that's it. That is our lesson on vector surface integrals. All right, so now let's move on to Stokes' theorem. So Stokes' theorem is basically a higher dimensional value of Green's theorem, right? We already know Green's theorem from previous sections, and that Green's theorem relates a line integral to a double integral over some region. But now we're working with Stokes' theorem. And what Stokes' theorem tells us is that it's basically, again, as I mentioned earlier, a higher dimensional value or version of Green's theorem. And the fact that we relate a line integral to a surface integral. And the way we do this is by first defining the curve over which we're going to use for a line integral. And so I'm going to start out by drawing a bit of a diagram to help us visualize this. So let's go here, draw that nice 3D coordinate plane. And what we're going to do here is that I'm going to go ahead and draw a hemisphere. Hopefully that makes sense. As always, my 3D drawing is not the best, but here we can say that this is our surface S, and then we're going to have our normal vectors, which from our previous section, we can just call that N1 to stick with the regulations and regulars that we defined in our previous sections. But basically, again, as I mentioned earlier, our normal vectors basically just define our orientation. And when looking at the surface, we see that at the bottom, right, as I am drawing right here, we have a curve C at the edge of our surface. And we can call, let me change my color to make this a bit clearer. We can call this curve the boundary curve. And the orientation of F will induce that the orientation of C is positive. And to get the positive orientation of C, let's basically just visualize ourselves, right? Well, let me draw a person here. We're going this way, right? We're walking around the curve. And as I'm walking around the curve, right, my head, let's visualize it as I'm going here. My head is going to be pointing in the same direction as these unit normal vectors. And basically that shows that is the positive orientation, positive direction of C. And basically, I guess that is our definition of a boundary curve. And once we define a boundary curve, right, we can say that our surface S, right, we can let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C. And the key word here is positive orientation, right? We want our guy to be, his head to be in the same direction of our normal vectors, right? And once we have our boundary curve C in that's positive orientation, right? We can let F be a vector field whose, another key point, whose components have continuous partial derivatives on an open region, which is R cubed, or all real numbers, or the 3D space, right? That contains S. And once all of these are met, right? Let me just write these down. S, we can say S is an oriented smooth surface. And we can say C, positive orientation, simple, closed, smooth boundary curve. And F is our vector field who has continuous US partial derivatives on the open region, R cubed that contains S, right? S. Once all of these satisfications are met, we can say the integral for the region C of f dot dr, Stokes' theorem tells us that this is simply equal to the double integral of S of curl f dot ds, right? And as I mentioned earlier, this is basically just making a line integral or relating a line integral to a surface integral. And that is all that Stokes' theorem is doing. It's making that relationship through this formula. And when looking at this formula, right, we already know that this integral right here is equal to this. And given our new integral, we know that double integral curl f dot ds is equal to curl f dot ds, right? And basically what Stokes' theorem says is that the line integral around the boundary curve of S of the tangential component of f, right, is equal to the surface integral over S of the normal component of the curl of f. And once we know this, right, the positively oriented boundary curve of the oriented surface S can be written, right? Stokes' theorem can then be written as, we can simplify Stokes' theorem. We can simplify the boundary curve, the positively oriented boundary curve, to daba S. That's what we're going to simplify the positively oriented boundary curve of S, right? We can simply simplify Stokes' theorem to be daba S of f dot dr. There we go. That is Stokes' theorem for us. All right, so now that we know Stokes' theorem, let's go ahead and apply it to a real problem. And the problem that I've chosen to go over in today's lesson is number 13 from the review sheets. So if you don't have that, that's completely fine. Let me just read it off, right? Let C be the curve of the intersection of the cylinder x squared plus y squared plus 9 equals 9, equals 9, and the plane z is equal to 3x plus 2y. And we're asked to evaluate f dot dr for the curve C, where C is oriented clockwise, right? When viewed from above from the positive x-axis. And we know that f of x, y, z, our vector field is xy plus z comma y cubed 1 plus sine z. And just note that I didn't write down the whole question here, right? I wrote down the key pieces of information that will make my problem solving journey a lot easier. So now let's go ahead and solve our question. So we know that Stokes' theorem tells us that the integral f dot dr for the curve at C is simply equal to double integral S over a region S of curl F dot ds. And one important thing to note here, right, is that, as I mentioned earlier, Stokes' theorem is simply just making or relating a line integral to a surface integral. And as we mentioned earlier, with the vector surface integrals, when we have a vector field, right, and we're trying to find the surface integral for a vector field, the normal vector is going to be important. And I want you to keep that in the back of your head as we're going to go ahead and solve this question. All right, so the first step that I'm going to take right off the bat, we know that in Stokes' theorem, the curl is very important, and we're already given our f value here. So I'm just going to go ahead right off the bat and start by calculating our curl f, which we know based on our previous problem solving experience just simplifies out to this. We already know our P and, sorry, let me just finish writing this down. We already know our P, Q, and R values from our given, our given F. So, sorry, let me multitask. Okay, so P is x y plus z, Q is y cubed, and R is 1 plus sine z. Boom. And from here, we can go ahead and find our curl. So we know that our curl, if you're not comfortable with this, let me write out a more simplified versions. Partial R with respect to y minus partial Q with respect to z, I plus partial P with respect to z minus partial R with respect to x. All right, we might have enough, yeah, I think we're gonna have enough space, hopefully. And then partial Q with respect to x minus partial P with respect to y. Okay, boom. That is a simplified version of this right here for finding the curl. And let me just remind you, this is our P, this is our Q, and this is our R. So when we do this, when we go ahead and simplify this, partial R with respect to y, we see there's no y in the R, so we can just say this is equal to 0 minus, let's go to the Q. There's no z in the Q, so that just comes out to be 0 as well, plus P. There is a z, that partial P with respect to z, we see it's just right here, so that would just equal 1 minus partial R with respect to x. There's no x here, so that would just be 0j plus partial Q with respect to x, no x again, so 0 minus partial P with respect to y. We see that that just comes out to be partial x, the partial of xy with respect to y, 0 minus x. Okay, boom. And then when we simplify that out, we get 0i plus j minus xk for our curl f. All right, so now we have our curl f portion of our Stokes theorem double integral. But now we need to think about the ds. And as I mentioned earlier, right, Stokes theorem is basically just relating a line integral to a surface integral. And as we mentioned, let's scroll up to our vector surface integral, right? When we have a vector, right, a vector function, we're going to have to find the normal vector as well in order to define our ds for our integral. So let's go ahead and do that. So we know that in our case, our z is equal to 3x plus 2y, and we know that the curve C is basically just the intersection with x squared plus y squared is equal to 9. So just for use in mind, help, I'm going to go ahead and graph this actually. Just a rough graph to better understand what is going on here. So we're going to have, on the xy plane, we're going to have a circle, radius 3, cylinder, right there. Boom, right there. And then we're also going to have the plane z is equal to 3x plus 2y. And on the xy plane, right, z is going to be equal to 0. So we know 2y is equal to minus 3x. So that's going to give us something along the lines of that. Let's extend that line and then draw the plane. Boom. We can draw that like that as well. All right. Just like a rough sketch, right? And then this is obviously going to be tilted like that. So sorry, the initial sketch was not the best. But it's going to be something like that, or at least that's what we're going to assume it to be like, based on the equation. And we see that it's going to intersect not like that, something like that, some tilted surface like that. All right, so now we have an understanding of what our curve C is, or in our case, what we're going to define as the boundary curve. Now, that is going to come into importance later on when we're defining our bounds for our integral. But right now, as I said, our main mission right now is to find our normal vector. And as we've already learned, we have z is equal to g of xy, which we already know comes out to be 3x plus 2y. And we can define our function f of x, y, z, as we did in the previous lesson, to be z minus 3x minus 2y. And then when we take the gradient of that, we are going to get minus 3, minus 2, 1. And then again, we need the unit normal vector, not just the normal vector. So we are going to divide by the magnitude of the gradient f. But note here, right? I'm not going to write out, just to save myself a little bit of time, I'm not going to go ahead and write out the magnitude of the gradient vector f, right? Because if we scroll all the way back up here, we see that inevitably, right, when we plug in our ds value and substitute it for our dA, this is just gonna simplify out to be the magnitude of our gradient f dA, as we already know, right? So regardless of if I define it or if I don't, I already know that that's gonna cancel out. So for right now, I'm just gonna keep it as the magnitude of the gradient f. Now, let's take a look at our orientation before we proceed, right? So in the question, where are we? They say that C is clockwise, right? But in this example right here, we see that C is going counterclockwise. And when it's that, we don't have to change anything regarding our question, right? But here we're given that C is clockwise. And when we realize that our C is clockwise, we realize that we need to change the orientation of our normal vector, right? In order to get, as we said, the positive orientation of C. Because right now, rather than pointing, let me change colors. Rather than pointing out like that, as you would expect, our normal vectors are pointing inwards or downwards towards our region E. Because of this, what I'm going to go ahead and do is that I'm going to take the negative, the opposite, in order to accommodate for this downward orientation, and hence, as we said earlier, to have the quote-unquote positive orientation of our normal vector. And when we do that, what we get is 3, 2, minus 1 over the magnitude of f. There we go. That is our normal or unit normal vector. All right, so now we have our normal vector and we also have our curl f. So let's start putting together the Stokes theorem integral or double integral, I should say, as defined by this equation. So we know we should have over double integral over some region f of curl f dot ds, which in our case, we're also going to need the normal vector. So curl f dot n ds. So when we do this, we still haven't defined our region S. We'll get to that shortly. But we know that our curl f, if we scroll up, is simply equal to this, which simplifies out to 0, 1 minus x. 0, 1 minus x. And then we're going to have to dot that by our normal vector, which up here we see is 3, 2, negative 1. Over the magnitude of our gradient times the magnitude of our gradient f dA. And as I said, these are going to cancel out. And when we do this dot product, right, we're going to get over double integral over the region S of 3 times 0 plus 2 plus x dA. So this is obviously going to become 0. So we get double integral over the region S of 2 plus x dA. All right, so now we have to go ahead and define our dA and our bounds. If we scroll all the way up here, right, we see that's the intersection of x squared plus y squared equals 9, which is a cylinder. But when we look on the xy plane, that comes out to be a circle. And because of that, I'm really tempted to use polar coordinates, which I think I'm going to go ahead and do. And when we look at the xy plane for the cylinder, right, we see it's a full circle. And as we saw from our plane right here, right, from our diagram, we see that it's still going to be a full circle. It's still going to be a full circle in that intersection. And because of that, we can decide or say the theta goes from 0 to 2 pi, and as defined by x squared plus y squared is equal to 9, r squared is equal to 9, r is equal to 3, we can say that r goes from 0 to 3. All right, now that we have our bounds, there's only one thing left to do, and that is to plug everything in and solve. So we know that dA, let's bring this all the way down here, dA, when we switch to polar, is equal to r dr d theta, which is what we're going to plug in. And we also know that here in our situation, as we can see right here, x is equal to r cosine theta. So when we plug everything in and simplify, we're going to get theta goes from 0 to 2 pi, r goes from 0 to 3, of 2 minus r cosine theta. Sorry, I'm going to have to move this over just because I'm going to run out of space. R dr d theta. Let's distribute the r just to make our life a little bit easier. Of 2r minus r squared cosine theta dr d theta. And now all we have to do is integrate with respect to r and then with respect to theta. When we integrate with respect to r, right, we're going to get the integral of r is 1/2 r squared times 2 just becomes r squared minus integral of r squared is 1/3 r squared. So 1/3 r cubed, my bad. 1/3 r cubed cosine theta from 0 to 3, d theta, d theta. As before, if we plug in a 0, both of these are just going to be 0, so there's no use plugging it in. So we get 0 to 2 pi of 9 minus 3 squared, or this simplifies to r times r squared. We know r is equal to 3, so those just cancel out. So we're going to get 9 cosine theta d theta. And then all that's left to do is simplify or integrate with respect to theta. And when we do that, we get 9 theta minus 9 sine theta from 0 to 2 pi. We know that sine of 2 pi is equal to 0 and sine of 0 is equal to 0. So this is just always going to be 0 for both bounds. So we have 9 times 2 pi minus 9 times 0, which comes out to be 18 pi, which is our answer. Now, before we can say this is the right answer, let's go ahead and verify this. Let's go ahead and make sure that our answer is right. So scrolling all the way up, let's see what the problem tells us. It tells us that C is clockwise. So that should tell us that we need to take the negative out of our normal vector, which we did do right here. So that's good. We also know that x squared plus y squared is equal to 9. So when looking at the xy plane, we're going to get a circle. So we should be using polar, which again, we did go ahead and do. Now looking at our f, we need to take the curl f, which we did. And just to verify that this is the right answer, partial r with respect to y is 0, partial q with respect to z is 0. So the x component should be 0. Partial p with respect to z is 1, correct? And partial r with respect to x is 0. So the y component should be 1 as it is. And then the partial q with respect to x should be 0 as it is, and partial p with respect to y should be x. So then 0 minus x is minus x. So the z component should be minus x. And then since we're doing it over vector field, since this is basically, as we said, we're just relating a line integral to a surface integral. Since we're taking it over a vector field, we must take the normal vector again, which we did go ahead and do down here. Z is equal to g of x, y. We define our function f, find the gradient, find the unit normal vector. And because it was downward oriented, we need to multiply by -1. Let's make that a bit more clear. Add a multiplication sign as well. Then all that was left to do was solve. And based on our calculations, that seems like the correct integration. So after we've checked, after we verified everything, it seems to be that we got the right answer. All right, so now that we've solved for this integral using our friend Stokes' theorem, we need to go ahead and verify that our answer is correct. And I think the best way to go about this is by solving the good old line integral the way we were first taught to. So let's start off. Let me write number 13 again. So we have our vector field xy plus z y cubed 1 plus sine z. And we know that C is the intersection of the curve x squared plus y squared is equal to 9, and the plane Z is equal to 3x plus 2y. And we want to find basically the line integral. And the way we're going to go about doing this is by first finding our function r of t, which in this case, we can say, we know that since C is bounded by the curves x squared plus y squared is equal to 9 and z is equal to 3x plus 2y, we can say that r of t is equal to 3 cosine t, 3 sine t. And 9 cosine t plus 6 sine t. And the next step we need to take, since in solving a line integral, a basic line integral, we know that this is equal to, from a to b, f of r of t dot r prime of t dt. We need to go ahead and find r prime of t, which we can find simply by taking the derivative of r. So derivative of cosine x is minus sine t, so minus 3 sine t. Derivative of 3 sine t is 3 cosine t, and derivative of 9 cosine t plus 6 sine t is 6 cosine t minus 9 sine t. And like that, we have our r prime of t. Now, the only thing we need left to solve for our line integral is finding f of r of t, which simply just plugging in these r of t values into our f equation, we get 9 cosine t sine t plus 9 cosine t plus 6 sine t, comma, cubed. So that would be 27 sine cubed t, comma, 1 plus sine of 9 cosine t plus 6 sine t. And so with that, we have our f of r of t and our r prime of t. And also, since we know that our function is a circle on the xy plane, we can say that our bounds for t are 0 and 2 pi. But when looking at this again, we realize that the question says that c is oriented in the clockwise direction. So to account for this clockwise direction, instead of counterclockwise, we are going to make this minus 2 pi in order to basically run the limit backwards in order to basically account for the clockwise. So now we have our limits, and we also have our f of r of t and r prime of t. So all that's left to do is solve this integral. I'm gonna copy this. Dotted with I'm going to make a new line just to make it a bit neater. And there we go. We have our integral. And surely, but surely, that looks extremely complicated. So I guess the first thing we need to go around doing is finding the dot product. And when we do this, the dot product we get comes out to be 0 to 2 pi of 81 cosine t sine cubed t minus 3 sine t times 9 minus cosine t plus 6 sine t plus 9 cosine t sine t, and all of this is in parentheses, and I'm going to start a new line just for clearness, plus 6 cosine t minus 9 sine t times 1 plus sine of 9 cosine t plus 6 sine t. And in checking our dot product, we realized that we made a little bit of mistake right here. And we also forgot to close out our parentheses properly, which I believe should be 3 right there, and dt. And this should be minus 2 pi. And this is our integral. Now, obviously, this is an extremely complex integral. And given the time constraints that we have, and the fact that we need to also move on to our next lesson and topic, I instead went ahead and solved this integral for us so that we didn't have to go through it step by step. And when we do this, the result we get is 56.5487, which lo and behold, we know that 18 pi is equal to 5487. So this we can say is equal to 18 pi as well. So in verifying our answer, we see that our Stokes theorem does verify out, and we do get the correct answer. So now let's move on to our next topic. All right, and finally, let's take a look at Gauss's theorem, which is better known, or I guess equally known, as divergence theorem. Now, we already know for Green's theorem, let me switch my color, my pencil color, just so we can distinguish between the different sections. So we know that we can rewrite Green's theorem to be as such, based on divergence. Sorry. And we already know this. We've already looked at this and proved it. And we know that in this situation, as previously mentioned in the previous section, C is a positively oriented boundary curve of the plane region D. But let's think, how can we expand this thinking to 3D? And the way we do this is through Gauss's theorem, in which we basically say the equivalent of the surface integral can be written in terms of the divergence of our vector function in 3D, or the 3D space. And in this situation, S is the boundary surface of our solid region E, as we went over in either sections 1 or 2. And because of this, because S is the boundary surface of the solid region E, we are able to say that this is true. And because this Gauss theorem, or as you may call it, divergence theorem, becomes true. Now, you may be wondering right now, what is this applicable to? And in specific, this is applicable to simple solid regions. And another requirement that must be met is the fact that, first off, the boundary E is a closed surface, but also based on the unit normal vectors, we want them to be pointing outward from E in the positive orientation. And hence we come to the divergence theorem, which basically says that let E be a simple solid region and let S be a boundary surface of E. And given that the positive outward orientation for E, let F be a vector field whose component functions have continuous partial derivatives on an open region that contains E. And if all of these are met, then this divergence theorem is true. Now let me write that down just so that we have a better visualization. So you want E to be a simple solid region, and we want S to be the boundary surface of E with a positive outward orientation, which we basically get by having the unit normal vectors point outwards from our region E. And finally, we want our vector field F to have component functions with continuous partial derivatives on an open region that contains E. And when all of these requirements are true, we are able to apply Gauss's theorem or divergence theorem. And basically what divergence theorem hence is able to say is under these given conditions, the flux of F across the boundary surface of E is equal to the triple integral of the divergence of F over E. And when looking at this, right, we can see that it makes our problem solving journey a lot easier. Because let's say we had a certain solid with multiple faces. Using just surface integrals and Stokes theorem per se, right? We would have to find the flux across each surface in order to find the total flux for that solid, right? But with divergence theorem, with Gauss's theorem, we are able to simplify that just to one triple integral because of it, and hence its applicability becomes very apparent. All right, so now that we know Gauss theorem or divergence theorem, I think it would be quite cool if we got to do an application of it as we have been doing for all the other topic areas for today's lesson. And in specific, I want us to look at problem number 10 on our worksheet. Now, as always, it's completely fine if you do not have your worksheet with you. But basically what number 10 is asking us to do is find the flux of a vector field f of x, y, z, which is defined by x comma z comma 0, out of the tetrahedron bounded by the coordinate planes. So coordinate planes and the plane x plus 2y plus 3z is equal to 6. Now, what I think I'm going to start off by doing is just graphing the tetrahedron that we are trying to find, I guess, the flux of, right? So let's graph this. Graph our 3D region. Boom, boom, boom. X, Y, Z. And basically, if we set y and z equal to 0, we get that the x-intercept is 6. If we set x and z equal to 0, we get the y-intercept is equal to 3. And if we set x and y equal to 0, we get the z-intercept is equal to 2. And this drawing itself is a bit off. Let me adjust the coordinates. All right. And then looking at the xy plane, setting z equal to 0, we get 2y is equal to 6 minus x, which, yeah, y is equal to 3 minus 1/2 x, which appears to just be this line right here. And then if we do that for the rest of the coordinate planes as well, we see that we get a tetrahedron like that, bounded below by the xy plane, bounded to the side by the zy plane, and finally bounded to the left by the xz plane. And that is basically the tetrahedron that we are trying to find the flux of. Now, looking at divergence theorem or Gauss's theorem, it tells us that we can find the flux for this tetrahedron simply by applying Gauss's theorem, which I'm going to copy this down to over here. This is the very simple formula that we must use. All right, so let's go ahead and find the divergence of F as our first step. And of course, we know that the divergence of F is just equal to delta P over delta X plus delta Q over delta Y plus delta R over delta Z. And in our case, we know that F is simply equal to Xi plus Zj plus 0k. And we know P, Q, R. So to find div F, we can simply look at this and say the partial of P with respect to X, we see that that's just equal to 1. Plus the partial of Q with respect to Y, we see that that's equal to 0. And then the partial of R with respect to Z, we see that that is again 0. So we get that our div F is just equal to 1. And looking at our integral right here for E, we see that that makes it a lot easier, as all we need to do is over this region of the tetrahedron, we just need to integrate the volume, or dv, or basically just find the volume of this tetrahedron. So the way I'm going to go about doing this is by setting up limits for my integral. So I'm going to say that for this specific problem, I'm going to find dv to be dz dy dx. And let's see what our bounds should be. So looking at how z is bounded, we see that, let me change my color. We see that below it's bounded by the xy plane, but above, the only thing that's really blocking it is this plane x plus 2y plus 3z is equal to 6. Hence, we can say for z, the limits are 0, and then solving for z in this, we have x plus 2y plus 3z is equal to 6. Let's double check to make sure that's true. That is true. Solving for z, we get 6 minus x minus 2y over 3, which comes out to be 2 minus 1/3 x minus 2/3 y. And we say that that is the upper bound. So that is the upper bound for our integral. And as mentioned above, our integrand right here is just going to be dz dy dx. We can stick the 1 in here just for a placeholder of sorts. Now looking at our y bounds, we're going to have to move over to the xy plane, which we had previously investigated a little, but let's actually draw it out this time. Sorry, let me draw that a little bit bigger, like that. So on the xy plane, setting z equal to 0, we see that that is a line on the xy plane that we should be trying to graph. And when we graph this function, y is equal to 3 minus 1/2 x, we see that setting x equal to 0, yeah, let me just write it out right here. y is equal to 3 minus 1/2 x. Setting x equal to 0 to get the x-intercept, we have y is equal to 3. And then setting y equal to 0 to get the x-intercept, we have 1/2 x is equal to 3, x is equal to 6. So we can just write that out there. So we have 2 points, 0, 3 and 6, 0. So all we need to draw a line on, the xy plane. And like that, we can just write that y is equal to 3 minus 1/2 x. Now looking at how y is bounded in this specific case, we know that y is bounded by the coordinate planes. So because of this, we can say that y's cross sections go from the x-axis to that line y is equal to 3 minus 2x. So knowing that information, we can say that the lower bound of y is 0, and then the upper bound is 3 minus 1/2 x. Let's move that a little just for some more space, like that. All right. Now going to the x coordinates or x bounds, the only thing we see here is that x is bounded by x equals 6 and x equals 0, which would be the y equals 0 axis or y axis. Sorry, not y equals 0, x equals 0, which would be y axis. So our bounds on x are 0 and 6. And from there, we see that we have an integral which we can calculate. Now I'm gonna copy this and move it somewhere else just so that we can have a little bit more clarity in our expression. We can go ahead and delete that arrow. Now, right now, the only thing we have left to do is to simply solve this integral. So starting off with z, never forget the equal sign, 0, 3, oh, looks like we forgot 1/2 here, 1/2 x of z from 0 to 2 minus 1/3 x minus 2/3 y dy dx. We know that if we plug in 0, we'll get 0. So the only thing we really need to plug in is 2 minus 1/3 x minus 2/3 y. And when we do that, 0, let's make this clear. 3 minus 1/2 x, 2 minus 1/3 x, minus 2/3 y dy, dy dx. Now, the next thing we have to integrate with respect to is the y component. And to do that, all right, so we're going to go 0 to 6, 2y minus 1/3 xy, since x is just a constant in this respect, and we know the integral of y is 1/2 y squared. 2/3 times 1/2 is just 1/3, so 1/3 y squared from 0 to 3 minus 1/2 x dx. All right, and simplifying that out, with 2 times 3 minus 1/2 x minus 1/3 x times 3 minus 1/2 x minus 1/3 times 3 minus 1/2 x squared dx. All we really have to do is bash those numbers out. We get 6 minus x plus 1/6 x squared minus 1/3 times 9 minus 3x plus 1/4 x squared dx equal to integral from 0 to 6. These cancel out to minus 2x, x minus 2x plus 1/6 x squared minus 3 plus x minus 1/12 x squared dx. We see that cancels out. This becomes 3. And adding these up, this is the equivalent of 2/12 x squared. So this would simply become 1/12 x squared. So simplifying that out, we get 1/12 x squared minus x plus 3 dx. And from there, all we gotta do is integrate with respect to y. Integral of x squared is 1/3 x squared, or x cubed, sorry. So 1/36 x cubed minus 1/2 x squared plus 3x from 0 to 6. We know 6 squared is equal to 36. So all we're left with is if one factor of x. So we get 6. Oh, and also as always, or not as always, but since we have 0, and if we were to plug in 0 for all of these values, it would just equal 0. We don't really need to write it out because we can assume the value is 0. 6 squared is 36, divided by 1/2 is 18. And then plus 3 times 6 is 18. These cancel out. We get our final answer is equal to 6. Now, in order to verify this answer, I don't want to do what we've been normally doing. Instead, I want us to think, right? If our div f is 1, that means that we're just finding the volume, let me change colors. The volume of our tetrahedron. So a way to verify our answer would simply be by finding the area of our tetrahedron. And the way that we can do this is by looking at this tetrahedron and realizing that it is in fact a pyramid, a triangular pyramid with a triangular base. So the way we could verify our answer is simply by finding the volume of a triangular pyramid. And so we know the volume of a triangular pyramid. Let me write verification. Verification, right? We know the volume of a triangular pyramid is volume is equal to the area of the base times the height divided by 3. Now, when looking at the area of our base, we see that on the xy plane, it's simply a right triangle with base 6, height 3. So we know our area would just be 3 times 6 divided by 2, which is 9. So that's equal to area of the base. And looking at our height, we see that that is simply the height of the z-axis, which gives us 2. So in order to find the volume of our tetrahedron, we can simply do 9 times 2 divided by 3, cancel out by a factor of 3. 3 times 2 is equal to 6. And lo and behold, our answers check out, meaning that via our verification, we got our answer right, which is amazing to see. So yeah, that has been AB Math for today. I hope you learned a lot, and I hope you took away a lot from this lesson. As always, if you have any questions, any concerns after our lesson, never fear from contacting me at my email, abhakta22 at andover.edu. I'm always open to getting any suggestions, any feedback, any comments. If you have any questions about the material today, always feel free to ask. And as always, well, let's change up the thickness. And as always, it has been AB Math. Thank you for coming, and I hope you have an amazing day.